Hello, everyone. Come on in. Come on in, everyone. Anybody have any questions while we're waiting for maybe a couple of other people to come in?
Professor, you did tell me to remind you that you were going to extend the due date for the Chapter 4 homework.
Oh, yeah. Thank you. Appreciate you reminding me on that. In fact, I actually have
And
it opened over
5-2, I
here.
think, because that might still be due on like the 25th.
Yeah, that help me. Thank you for that. So I'm going to my lab and mastering. Let me do that right quick while I'm on here. Go to my lab and mastering. Anybody else have any questions while I'm doing this? Let's admit that person. Go to assignment. And chapter 4 was due on 9/18, conceptual, and the homework was. So what I'm going to do is I'm going to give you to the 25th on both of those. So if anybody needs more time to do chapter 4, I'm giving you a little bit more time just because of the difficulties we had. So both of those have been moved to 9/25. Chapter 5 is 9/25 as well. I'm actually going to push the homework back to the Wednesday just to help y'all have a little bit more time. So that should do it now. All right, that's taken care of. Anybody else have any questions or comments or things they want me to help them do or whatnot? All right, well, we're going to finish up chapter 5. And basically we had started with friction last time. I'm actually trying to roll through my notes and see what all we did. And that's not it. Oh yeah, I remember where it's at. Dull. Okay. So yeah, I'm trying to look back through my notes and see exactly what we did to make sure I was on the same page. So let me look here on the 19th. Yes, we did the Atwood machine. I did the train of boxes. I did an inclined plane Atwood machine. So yeah, okay. So what I didn't get to was circular motion. And that's what I want to do now. In fact, though you haven't seen it yet, I have actually taken the time to create an extra credit assignment for this week. It should be in module 5, module for week 5, and it's still not arrived yet. I copied it over from another course, but it should be under a little banner that says extra credit. And basically, it's me asking you to try to do the same thing that I'm getting ready to do now, which is I'm going to start off with a vector. It's actually a vector as a function of time. That's a position vector, and therefore we're going to call it R of t with a vector symbol over it, of course. And that vector, you can actually, that's one of the things I'm asking you to do, is to actually plot the vector at t equals 0, at t equals, in this case, you can, if you have a hard time with dealing with symbols, you can just say the period of the motion. In other words, the time required for it to go from here back to here again is going to be 8 seconds. You can do that if you want. But what I'm going to say is you're going to plot the vector at t equals 0 seconds, then at t equals t over 8, and then at t equals 1t over 4, and then at t equals 3t over 8, and then at t equals t over 2, and so on and so forth. So basically, every eighth of a period, you're going to draw this vector. And then I'm going to ask you to do the same thing for the velocity vector. And then I'm going to ask you to do the same thing for the acceleration vector. And of course, you're going to calculate the velocity vector from the position vector and the acceleration vector from the velocity vector. So let's see if we can actually do that. I'm going to try to share a screen right now. I'm going to actually work it for you. And in honesty, you can get the extra credit just by copying what I did, but you're losing an opportunity to make sure you know how to do stuff if you do it that way. So it's all up to you. I don't mind giving extra credit. And I even don't mind people taking advantage of it. It's a shame because it would harm them as opposed to helping them. And the whole purpose of me making up extra credit is, of course, to help people. So let's see if it's going to take it. Of course, it's not going to take it because it never takes it. Isn't that so helpful? All right, I'm going to go try to go here again, turn off my Wi-Fi. This is just so fun. I wish I could do this 3 times a day. Now let's see if it'll share now. What the heck? Okay, I'm back on the Wi-Fi. Go back here again. Go to share. Go to Zoom. Still says it cannot connect. Oh, that's helpful. That's super, super helpful. Let's say stop share. Now I'm going to disconnect my Wi-Fi again. I'm sorry about this, folks. I really don't know why it's doing this. It shouldn't be doing this. I'm going to reconnect my Wi-Fi and get a check mark. I now have a check mark. I'm going to now do share. iPad, iPhone via AirPlay. Now I'm going to share screen. Okay, so that part's working. All right, so here it is. So what I'm going to tell you is this vector, I've already worked out the details of it, but basically what we have here is R as a function of t is equal to R, that's a capital R, and it's a constant that we know of, cosine 2 pi over t I hat plus R sine 2 pi over capital T j hat. Okay, t equals the period of motion. In other words, that's the time it takes for this thing to complete one circle. Regular lowercase t, of course, is just the time. And in fact, you could write 2 pi over t is 2 pi times the frequency. And that would be the same thing, only in that case, the frequency f is 1 over the period. And of course, that would be in units of hertz. So the period would be in units of seconds. And the f would be in units of hertz, which is cycles per second. It's another way of interpreting that. So first off, what we realize is if you actually do a plot of this, if you take t equals 0, you can see automatically that you're going to get r for the I component and you're going to get 0 for the j component. So basically at t equals 0, the vector is r units long, pointing from the origin to the x-axis. Along the x-axis to a point r. So basically the particle is going to be on the x-axis, a distance r away from the origin. And then if you look at t over 4, that basically becomes 8 pi times t. That's going to actually give you a vector that's pointing straight up and has a length r. And if you go to pi over or t over 2, then that's going to give you a vector pointing to the left that's r units long. And if I go to 3/4 t, it's going to give you a vector pointing straight down. And then if I go to t, it'll be the same vector as we started off with. So that's what that r vector is. And that's why I'm asking you to verify that graph. Now, I'm also going to say that v of t is dr over dt, because we've learned that already. That was our chapter 2 material. Now, if I take the derivative of cosine, the derivative of cosine is negative sine, but then I got to use the chain rule and take the derivative of 2 pi over t times t. So I'm going to get negative r 2 pi over the period sine 2 pi over the period times time, and that's in the I hat direction. And then the derivative of sine is cosine, so I'm going to say plus r, again, 2 pi over t times cosine, excuse me, yeah, this one will be cosine of 2 pi over t times t, and that's in the j hat direction. So hopefully y'all can see that. Does everybody follow the steps I just took there? Does that make sense to everyone? Now, if you notice, this this vector is just a vector with a component in the x direction, actually the negative x direction, and a component in the positive y direction. Those two are perpendicular to each other, so the Pythagorean theorem applies if I want to know the magnitude. So the magnitude, you might think, is a function of time, and we would write the magnitude as a vector symbol with the absolute value bars over around it, or you could just write it as v. But either way, it's going to be the square root of, now we're going to take everything the two terms have in common, and since I'm squaring each term, this is going to become r squared, and this is going to become 2 pi over t squared. And then that's what I factored out. Then I have sine squared 2 pi over t times t plus cosine squared 2 pi over t times t. And I think you all can tell me what sine squared plus cosine squared is. Anyone?
1.
It's 1. So in fact, we end up getting the square root of r squared times the square root of 2 pi over t squared. So it's just basically going to be, and watch how I write this. I want to write this as 2 pi r over t. Does anybody know what 2 pi r is relative to a circle of radius r that we just said this r is tracing out? Yeah,
It's
remember
the
what?
circumference.
Exactly. So this is circumference divided by the period. So in other words, it's the velocity is just the distance divided by time as we expected. And in fact, it doesn't depend on time. So it must be a constant velocity. So that's really what the constant velocity is. It's just 2 pi r over t. And that's going to come in handy a little bit later. Now I'm going to calculate a of t. And that, of course, is dv over dt. So now I've got to take the derivative of v of t. I see that the derivative of sine is equal to cosine, and the negative is going to stay there. So now I'm going to have negative, whoa, it just changed to eraser again. Negative r, now I've got 2 pi over t squared cosine of 2 pi over t times t I hat. Now the derivative of cosine is negative sine, so now I got a minus there as well. So that's r times 2 pi over t squared times the sine of 2 pi over t times little t j hat. So that's the acceleration as a function of time, and you're supposed to graph that as well. And what you're going to get is that, like, at t equals 0, the position vector points from the origin to the right along the x-axis. At t equals 0, the velocity vector points straight up like this. And then at t equals 0, the acceleration vector points towards the center of the circle. And in fact, it's called the centripetal, P-E-T-A-L, acceleration, because it is a center-seeking acceleration. Okay? There's no such thing as centrifugal, F-U-G-A-L, acceleration. People think there is, and it feels like there is, but really that all that is like you're going straight, and then all of a sudden you take a 90-degree turn, and it feels like you're going to fall out of the right-hand side of the door. Well, that's just your body wanting to obey Newton's first law and keep going straight in the direction it was going, but you're turning, luckily, and the friction is sufficient, and the door lock is sufficient to keep you from going the other direction. So that's what that is. Now I'm going to do the exact same thing and calculate the acceleration's magnitude, which could in principle be a function of time. So, but again, you see it has a component that's parallel and pointing inward in the negative x direction. And there's another one that's pointing negative y direction. They're perpendicular to each other. So I'm just going to use the Pythagorean theorem. And I'm going to write the things that are in common. I'm going to have to square each of those. So the r is going to become squared. And the 2 pi over t is already squared. So that's going to become to the 4th power. And that's common to both of those terms. So I'm going to that's been factored out. Now I'm going to get cosine squared 2 pi over t plus sine squared 2 pi over t. Close that square bracket, put that over here, and you can see again we got cosine squared plus sine squared, which is equal to 1. And this time we get something a little different. We get r times 2 pi over t times 2 pi over t. Now that's a little weird. It's pretty close to a velocity. In fact, you could write 2 pi r over t, in which case this would be a velocity, but you still have 2 pi over t here. Well, one thing you can do is multiply by r over r. So what I'll do is I'll multiply by r over r, and we're allowed to do that because r over r is what?
It's 1.
It's 1, so we can do that. So now I'm going to have v times 2 pi r over t times 1 over r. Well, you see this again is v. Whoa. This again is v. So now we finally get that this is v squared over r, and that's called a centripetal. Now you can actually do this another way. Your book does a derivation of the centripetal acceleration a little differently, and that one's okay. It's pretty ingenious. I like it, but I really don't like it as much as this one. I like this one because this allows you to use your calculus and allows you to not only that, see how you can sort of make up a function. I made that function r cosine 2 pi over t, and I had an r sine 2 pi over t. I made that up just by trying to think of something that would be going in a circle. And by doing so, I was able to actually figure out that the centripetal acceleration is in fact v squared over r, which is a thing that we're supposed to learn in chapter 5 anyway. So now we have a centripetal is equal to that. We also know that v is equal to 2 pi r over t, and that's a constant velocity. So circular orbital motion, for instance, like if the distance between the center of the Earth and the center of the moon were actually always a constant, then that would be a circular orbit. It's actually not. We have times where the moon's a little closer, and we have times where the moon's a little further. But if it were really a circle, that would mean the moon would be orbiting us in a perfect circle and would be doing so at a constant velocity. Okay, so that's what comes from realizing that in order to get a circle, you have to have a constant velocity, and it's going to be v squared over r is the acceleration. Okay, now if you wanted to, for instance, not necessarily follow a circle, maybe you want to follow an ellipse or an oval or something like that, all you have to do is just force yourself to speed up every now and again. So then if it's non-uniform motion, this was uniform circular motion. So I'm hesitant to put the word circular in it. I'm just saying it's non-uniform motion, whereas this was uniform circular motion. If you do that, then A is actually going to become basically dv dt. Notice I did not put a vector symbol on that. It's just the magnitude of the velocities derivative with respect to time, say in the I hat direction, or actually let's say in the v hat direction. That'd probably be the best way to say it. V hat. Let me erase some stuff here where I just went crazy. Okay, so this is going to be in the v hat direction, and then minus v squared over r in the r hat direction. Notice I've got the negative there, and that negative is telling you that it's actually pointing in towards the origin. And what you have is a tangential plus a centripetal. Okay, so that's the general expression for accelerated motion that may or may not be in a perfect circle. If it's in a perfect circle, then dv/dt is going to be 0. But the main thing is we're seeing that it's actually dv/dt is you hitting the accelerator. So in that top part, this is you going into a big parking lot, turning your steering wheel at some point, and let's say tying it off so it stays in that particular turning direction, and then locking your cruise control and say 30 miles per hour. That is the uniform circular motion we're talking about. But if at any time you decide to hit the accelerator, well, then you're going to change that speed, and that speed is going to cause you to, for instance, speed up, and your distance away is actually going to, in fact, increase from the center. So if you're doing that and you're going like this, if you all of a sudden speed up, then the force of attraction that's needed to keep you in a circle is now insufficient, because v squared over r is what the force was, and now you've just changed v, so v squared over r got larger, and unless you have that much more force to give, then you're not going to do it. But if you're talking about an orbit, then you're definitely locked in, because the orbit has a gravitational force pulling it that's actually proportional to the product of the masses and inversely proportional to the square of the distance between them. And for that particular velocity, you're locked in and you're going in a nice circular orbit. But for instance, if you, let's say you're in a circular orbit over the Earth, and you're in a space shuttle type vehicle, and you're in more or less the same orbit as the International Space Station, and you see the International Space Station, in fact, right in front of you, some maybe a couple hundred yards or something like that, your first instinct would be hit the accelerator. Well, if you did that, you would speed up and, in fact, lift up like this. And then you couldn't really get to the shuttle. In fact, the right response is slow down. And by slowing down, it's going to force your orbit to come smaller and smaller. And that's going to increase your speed until you get right up under it. And then at that point, you can just speed up and slowly lift up to the actual bottom of the International Space Station, say. So that's some of the weird stuff that happens with this type of dynamics. But the main thing is realize that circular motion means constant velocity with constant radius. If you go hitting the accelerator or the brake, you're definitely going to end up changing the radius and the V. Any questions on that? Now, I tell this story. It's this kind of tragic story, or it's definitely a tragic story and a sad story, but I tell it, and this is a nice thing to know, okay? V squared over R is something that's important, and let me tell you why. So I think this was in the late 90s. I saw 60 Minutes, and this was, quite early. People do this stuff all the time nowadays. You can see it on Instagram and TikTok and Twitter and Facebook and all that stuff. People would just go like out in the Utah desert and just like tie a rope to something and swing off these big arches and cool stuff like that. That's kind of fun. I mean, I get it. I love that. This guy did this like I said, it was probably the late 90s, might have been the mid 90s. And he was going around and doing this. And then he said, hey, let's go. They lived in California. He said, hey, let's go do this off the Golden Gate Bridge. And they're like, yeah, that's cool. Well, the big thing about the Golden Gate Bridge is people actually commit suicide by jumping off the Golden Gate Bridge. It's high enough where you can die from just jumping off the Golden Gate Bridge. So that's a very high bridge. So he goes and says, okay, well, I got 6 people doing it. And in fact, it was like 5 or 6 people that were in a group, and they all were wearing like rock climbing harnesses, and they were all affixed to each other. And then that unit that was affixing them to each other was affixed to a cable or a chain or something like that. So he goes to the local hardware store. He's now weighed everybody. And let's say, and I'm just making up these numbers, let's say he determined that the total weight of all the people was 2,000 pounds. Okay. And he goes to the hardware store and he found some cable or some chain or something, and it was like 3,000 pounds. He's like, oh, great. That'll even give me a margin of error, a little safety factor. That's nice. So he buys that. And then he sets everything up, and they start to jump off the Golden Gate Bridge, which looks something like this, say. And they've got a rope, and it's more or less hanging like this. And here's all the people. Okay. Well, as they start to swing down, the force acting on it really is mg, where m is the sum of their masses, and then also a tension T. But here's the problem, and I'm going to draw it at the bottom to make the biggest effect. But in fact, I think they only made it to about 15 to 20 degrees of a swing before all hell broke loose. So what actually happens is they would swing ideally in some radius r, say. And when they got straight up and down, what you would have is a tension pointing straight up and a mg pointing straight down. The problem is this is not a particle sitting still. This is a particle. In fact, it's actually a number of people, and they are actually accelerating towards the center of the circle. Well, that's what they're doing if they're wanting to maintain a circle. So if you work this out, the summation forces in the y direction is equal to mass times acceleration in the y direction. Well, the forces are T minus mg, and that's got to equal to m times v squared over r. Well, you could use conservation of energy and stuff like that if you wanted to figure out how fast they're going at the bottom, and that's fine. But we don't really need that right now. What we need to realize is that the tension is going to be m times g plus v squared over r. So the tension has it has something to do, of course, with the weight, but it's hardly right to say it's just the weight. And in fact, his safety factor was nowhere near big enough. And like I said, the line popped somewhere about 15, 20 degrees into the swing. One person hit a boat, it's a quadriplegic for the rest of their life. Other people were really seriously injured. I want to say one person died. I mean, I don't want to say that, obviously, but I think one person actually died. But all this came from just a little lack of knowledge of physics. If you want to swing, it's not sufficient for the swing to just hold you. The swing's got to hold you and be able to provide the tension to keep you in a circle. So any questions on that? All right, so that's a typical example. Now I'm going to do another one. And this one is, I'm going to imagine we are transportation engineers and we are making an exit ramp. And we want the exit ramp to be sloped such that if I go off on this exit ramp doing the speed limit, let's say I'm going to mark the speed limit as 35 miles per hour. And if I go around that turn at 35 miles per hour, even if that turn is a complete sheet of ice, I want my car to still, or whoever's car, to still be able to make that turn without sliding. Okay. Well, the trick is, in order to make a turn, you've got to have a centripetal acceleration. And on a flat road, your centripetal acceleration comes from you turning the tires and the tires' friction being sufficient to hold it. If you try to take too sharp of a turn, R goes too small, in other words, then V squared over R becomes really big. And then the centripetal force required, which is that times M, becomes really big, and you skid, you slide out, basically. Okay. So what we're going to do is say, what is the,
Professor,
yes, sir.
what is R? Is that just a constant for what?
It's the radius of the circular path that you're taking.
Okay.
And believe it or not, that's really all you need. Like I've actually worked as a civil engineer, or work with civil engineers doing civil engineering, and we'll lay out neighborhoods. They're called planned urban developments, and we'll design streets and stuff like that. And all you have to do to have that street created and reported is basically you're going to say that street has a certain radius of curvature, and that's the R that we're talking about. It doesn't have to be a perfect circle. It can be an arc, but sure enough, when you go to spec that, you're going to say some part of it's a circle of radius R, and then right next to that touching, it's a circle of radius different R, and next to that's the circle of radius different R, and you sweep out different angles, and you can get any kind of elliptical shapes or whatever you want by doing that. But yeah, that is actually the only parameter that's really needed in laying out streets in AutoCAD. You just need like a radius of curvature and through what angle you want to turn. Like, do you want to make a 90-degree turn or a 45-degree turn, that kind of thing. So the question here is, what is the proper banking angle theta for a car traveling at a speed of v? Okay, so I'm going to work this out. This will be a formula that you can use over and over again for any v's, but I'm going to work it out in terms of just the symbol v, so that way it'll work for all v's. Now, I didn't list the mass of the car. That might be a problem, but whenever you're faced with such a problem in physics, what you do is you assume the mass is, say, m, and you work it out, and hopefully somewhere along the lines it'll cancel out and show that you don't need it. If it does cancel out, then that means it actually is unnecessary, and in fact the answer is universal to any mass you might have, which is the ideal scenario for transportation, because you wouldn't want to have one exit for Mack trucks, another exit for F-350s, another exit for F-150s, another exit for regular cars, and then another exit for Honda Prius and Cubes and stuff like that. So what I'm going to do now is I'm going to draw the incline. Okay, that's a really big incline. I just did it for dramatic effect. Okay, and actually, if you've been to a NASCAR race, or at least to a NASCAR racetrack, you will be surprised at actually how steep those angles are. Like I rode by Daytona a couple times, and I was really surprised at how steep that was. So the car would be sitting something like this. There's one tire, there's another tire, there's your bumper, there's your hood, there's your cab, something like that. And in fact, what you have acting on it is by a free body diagram like this. So I'm going to draw a free body diagram. Well, that was crap. I'm going to draw a free body diagram like that. Okay. And now I'm also going to draw the incline as if it were this. Okay. Again, this angle is theta, which is going to come in handy. Now, the object is going to be just this little dot right here. And it has, let's say, a mass m. Okay. The forces acting on it are, in fact, going to be a negative y force, since this is the y-axis and this is the x-axis. It's going to be a negative y force equal to mg. And then there's going to be this normal force that's perpendicular to the surface. That's what normal forces are. That's going to be Fn. Okay. Now, this is a case where I could have actually tilted my axis, but I know from experience that's not a good thing to do with this problem. Okay. So it's basically because the acceleration that this car is going to have to exhibit has to be towards the center of the circle, and in fact has to be along the x-axis. So if I tried to do it with a tilted coordinate system, then I'd have an acceleration that would have two components, and I'd have twice as much crap to do. In principle, you could use it, but it just wouldn't be fun. Okay. So what we've got to figure out now is what is the summation of forces in the y direction, summation of forces in the x direction, that sort of thing. So first off, I'm going to take the Fn and I'm going to convert it to a positive x component and a positive y component. So the positive y component is right here. And the positive x component, dang you. There you go. Fix that. And the positive x component is going to be right there. Man, why you gotta be a jerk? I like my drawings coming out nice, and the OCD is really killing me here. Okay, that's the positive y component. Now what we got to figure out is what's this angle? Well, let me give you a little brush up, if you will, in geometry. So it turns out that this, if you look at the y-axis, you can make a right triangle out of this, and this would be the right angle. And you know that the sum of the angles inside of a triangle is 180, and you've already accounted for 90. So this one must be added to theta to give you 90. In other words, they're what we call complementary angles. And that CO in complementary is the reason there's a CO in front of sine to make cosine. So the sine of theta is the same thing as the cosine of the complementary angle to theta. So in fact, this angle over here would be 90 minus theta. Okay. Now that's kind of helpful. So that's one way we can see that angle. Then we realize, wait a second, the line, marking the x-axis and the y-axis, that makes a 90-degree angle. So this angle between the blue line and the red x-axis, that must be theta, right? Now you realize, wait a second, the blue line and the normal force are perpendicular to each other. So theta and the angle inside of Fn, they have to be complementary angles. So this guy is going to be 90 degrees minus theta. Well, that's a right triangle as well. So that means this angle up here could be theta. So that's one of the many, many ways you can do it. You could also do it by realizing that I like to think in terms of like a railroad track. So if you imagine a railroad track, there's one track, there's one track, and then I lay a piece of rebar across it. Okay. If the railroad tracks are parallel, and only if they're parallel, then alternate interior angles are equal. What does that mean? Well, alternate means on opposite sides of the bar, and interior means between the trailing tracks. So alternate interior angles are equal, and you can see that in fact theta being between the blue line and the barely drawn red line, and then theta between the road line and the x-axis, they're alternate interior angles. So that's another way I could have reached that conclusion. It turns out also that corresponding angles, which means angles that are in the same spot, basically. And an example of that would be this guy. Whoa, damn it, I hate it doing this. Okay, so if I drew an angle right here, that angle corresponds with the first angle I drew. But another way of getting that angle being the same is if you look right here, that's a vertex. So these two are called vertical angles, and therefore they're equal as well. So that's just some geometry you can use from time to time. You don't have to, but you're always going to have to be able to figure out angles like this problem's doing here. So now that we have done that, we figured out that angle theta is up there. Now I can say that the vertical component of the normal force is in fact going to be Fn times the cosine of theta. And the x component is going to be Fn times the sine of theta. Does everybody agree with that? Or at least, does it make sense to you? Anybody question it or need help understanding it? All right, well, I'm going to move on then. So I'm not going to go and write, summation forces all the time. I'm just going to write y now. So I'm going to say, all right, we're doing the problem. So, and all of this, of course, started as a solution. So for the y coordinate, we have Fn cosine theta minus mg. And we don't think the car is going to be bouncing up and down in the y direction. So we might as well realize that that acceleration is 0. And in fact, from that, we can find that the normal force, check this out, this is entirely different. This is something you've never had before, is mg over cosine theta. So your book was right. Your book said, hey, the normal force is not always mg. They said caution or warning or something like that. I think it was caution. The normal force is not always mg. You had found, for instance, on the inclined plane, the normal force was mg times cosine theta. Well, this is a case where it's not even that. It's something different. So I'm going to go ahead and circle that off and call that equation 1. Now I'm going to do the x direction. Well, what you got to realize here is in the x direction, this car is not moving. It's just like the people on the swing. They're not sitting still. This car is not sitting still either. I think I said it's not moving. That was a misspeak. But this car is not sitting still. This car is actually accelerating to the right because that's the only way it can follow a circular path. So in this case, we're going to get x. The only force acting in that direction is in fact Fn sine theta. So Fn sine theta has to be equal to m times a centripetal. Okay. So that means Fn times the sine of theta is equal to m times v squared over r, where r is the radius of the turn. Okay. In other words, we have to know that. I should have written that in the original question, but I forgot to because I got sidetracked in the middle of the sentence. Okay. So if we want to figure out what this angle theta is, we've got to deal with this equation 2 here as well. Okay. So what I'm going to do is plug 1 into 2 and solve for theta. So here we go. I've got Fn. I'm going to replace that with mg over over cosine theta. And then times sine theta from equation 2. And that's equal to mv squared over r. And we see right now that that m cancels out with that m. So we're lucky enough to realize, oh, it doesn't depend on m. Okay. We might also realize that sine over cosine is a trig identity that comes in handy. Anybody know what sine over cosine is?
Tangent.
Yep. So we're going to say tangent theta is actually equal to v squared over gr. So really all that matters to banking a curve is the gravitational acceleration, the velocity, and the radius of the turn. Okay, so obviously this formula would be altered a little bit if we were making a bank curve on Mars, because g there is different from g here. But it also changes when you change the radius of the turn. In fact, the angle's got to go up when you increase or decrease the radius r. And it's also got to go up when you increase the velocity. Okay. So that's really an expression that gets you theta without friction. Now you could go and work this and assume friction acts in a certain way. In fact, if you go around this curve after you've designed it for a velocity of say 35 miles per hour, if you are in a snowstorm and you go around such a curve at 35 miles per hour, everything's going to work great. It'll be awesome. But if you're a little apprehensive and maybe you go in at 25 miles per hour, then there's actually a real risk that you will slide down the incline and hit the inner guardrail. And if you get a little cocky and try to do it at say 45, you're probably going to slide off the top of the curve and hit the guardrail on the outside. So if you're driving in the snow, it's best, at least on the straightaways, to try to probably do a little bit less than the speed limit to give you more time to stop, give you more control, that sort of thing. But when you get to exits and stuff like that, you want to try to do the speed limit. Okay. Not a lot less and definitely not anymore. Okay. So we've got that. And in fact, let's take a real life example. Say theta equals question mark for V equals 35 miles per hour and R equals 100 meters. Let's try that. So first off, V equals 35 miles per hour is a bit of a pain in the butt, but luckily I can convert that rather quickly. You know how to convert it. The way I normally do it is I convert first from miles to feet per hour by multiplying by 5,280. And then I convert that to inches per hour by multiplying it by 12. And then I convert inches to centimeters by realizing 1 inch equals 2.54 centimeters. And then I convert from centimeters to meters. And then I convert from hours to seconds. Okay. So in this case, I'm going to say 35, and I'm going to convert that. I'm going to say the units are in meters per second. Or excuse me, miles per hour is the units now. And I'm going to convert that to meters per second. And my calculator automatically does this, which is kind of nice. And it gives me 15.64. So 15. V equals 15.64 meters per second. I've used 2 extra sig figs there. Theta is going to be equal to the tangent inverse of, somebody just came in, the tangent inverse of 15.64 squared over 9.80 times 100. I'm leaving the units off because obviously I'm kind of tight for space in this little corner of my iPad. So now I can do this calculation. I'm going to say 15.64 squared and then I'm going to divide that by parentheses 9.8 times 100. And that gives me 0.2496. 0.2496. So theta ends up being the inverse tangent of that. So I'm going to say trig function inverse tangent of 0.2496. And that's going to give me 14.01 degrees. Okay. Any questions on that? All right, so that's the way you frequently use the v squared over r. Obviously, if you're wanting to work out, you know, how an orbit's going to work or something like that, you would need v squared over r. If you want to take a bucket, perhaps y'all did this as a child, you take a bucket, it's filled with water or sand or something, and you spin it vertically. If you spin it at the right speed, then it can get upside down and no water will pour out of it, or no sand, whatever you do it with. It's more exciting with water, or actually it'd be really exciting with like uric acid where it could blind you. But obviously there's some danger in that. But if you did that, then you could really test your faith in science. And basically all it takes is to solve the problem of something going in a circle and figuring out how fast it must go so that the substance would stay in. So I'm thinking we maybe should solve that. We have until 6:40. I've got to keep remembering that because I'll let you guys out early before. So let's imagine that I'm going to have a object of mass m on a rope of radius r. And it's going to, in fact, go in a circle. Thank God, that looks better than what I had. It's going to go in a circle of radius r. Okay. Now, what I got to realize is when I get to the bottom, if I'm holding this by a string, there's going to be a certain tension. So let's examine. Okay, let's not do that at all. Let's examine speed and tension at the top, the side, and I use Oxford comma, and the bottom. Okay. So I'm going to say solution. So the solution is going to be, let's start off with top first. So my free body diagram is going to look like this. Okay, I'm going to have a mass right here. And in fact, the forces acting on it are going to be the tension T and the weight mg. Okay. Now this object is actually accelerating this way with a equal to v squared over r. So summation forces in the y direction is going to give me that mg plus t is equal to mv squared over r. So we get that t is actually equal to mv squared over r minus mg. So in other words, the mg is actually accounting for some of the necessary acceleration. And that makes sense, right? The earth is pulling it down, and when you're going in a circle vertically at the top, the ball or the bucket or whatever wants to go to the left, but it's got to be pulled straight down to stay in a circle. So that's doing it right there. And in fact, you get T top is equal to M times V squared over R minus G. That's one result. Okay. Now, as that tension goes to zero, that's really when the water is going to stay in the bucket. Okay. If you go, if you provide more tension than that and more speed than that, then you can actually keep the water in as well. But that's sort of the crux point, is when that T top is V squared over R is equal to basically G. Okay. Now, if we look at the bottom, now we're going to say the speed, in fact, as I'm taking from the previous line. Actually, let me go ahead and go back to red on that. So from this, T going to zero implies that basically V has got to equal the square root of GR. So that's the minimum speed that it has to have to actually maintain that circle and for the water in the bucket or the sand in the bucket not to pull out or pour out. Okay. At the bottom, now I'm going to draw my axis again for my free body diagram. So it looks like that, and I'll have a little object right there, say. And in this case, I've got a tension pulling up. And I've got a weight pulling down. And in fact, this object still has to be accelerating at v squared over r. So the y direction for this one gives me t minus v squared over r, or excuse me, I don't know why I wrote v squared over r in there. That's just stupid. Excuse me. T minus mg is equal to mv squared over r. Okay. So in fact, you get that t has to be equal to m times g plus v squared over r. But remember, v minimum is equal to the square root of gr. So if you combine these two, you're going to get that the tension in this case is going to have to be, if I put g square root of gr in that v slot, that's going to give me gr in the top divided by r. So it's actually going to be t is equal to 2mg. So that's what the tension is going to have to be if you've got it going fast enough to keep from spilling anything. I don't know what's happening here. Something crazy is happening with my notes, and I don't know why. Go away. Ugh. Somehow I just opened up a text box and I don't know why. Maybe I can do undo until it goes away. Damn it. Everything's going away except what I want. So v min equals the square root of, I think it's a little window that allows me to open up, but for some reason it's been a butthole. So v min is equal to the square root. Why won't it let me write? Anybody have an iPad that uses OneNote can tell me what the crap's going on? Oh, I got it. Never mind. Okay. This is equal to square root of gr. So combining this and combining this, what we found was t is equal to m times g plus g over r, or times r over r, which equals 2mg. So that's a necessity. Just making it go just fast enough to not spill is going to cause the tension to have to be twice as big as the mass at the bottom. Now on the side, what's going on? So let's say left side. So for the left side, I'm going to draw a free body diagram again. And I have a little mass here, m. Now what's going on in this case is I've got a t going to the right, which is a positive direction. So I'm going to say this is the tension T, and I have a mass, or a weight that is, pointing downward that's equal to mg. But in this case, the object's got to have an acceleration a equals v squared over r. Okay. So you can see, because t and mg are perpendicular to each other, they're not going to have really any effect on either one. So what we have to do is we'll say for the y direction, we're going to get basically mg is the only force acting that's acting in the negative direction. So negative mg is equal to m times a. So we see that, in fact, it's going to try to speed up there. We're going to find that a is actually equal to negative g at the left. Okay, so that's not necessarily that interesting, but the x part, let's see what happens with that. Well, in that case, you get t pointing in the positive direction, and that's got to provide the acceleration in the positive direction, which is v squared over r. So in fact, the tension just got to be nv squared over r for that case. So nothing all that exciting, but that's how you do this sort of analysis on different parts. Let me get rid of this v here. There you go. Now I'm going to write v squared a little bigger. I don't know what happened there. Come back here. So v squared, dang it. Oh, it's making me mad. Okay, and now I can switch back to the green pencil. That'll be that. That'll be that. Okay, so that's the sort of results we have. Now, one thing that could actually matter on, though, is if you want to talk about your weight, say at the equator versus your weight at the North Pole. Okay, so in this case, we might draw the Earth like that, and we'd say, okay, you're standing on a scale. You're standing on a scale. The scale is going to look like this and got a number on it, and then a plate, and then there you are. Okay, and then you're also going to stand on a scale here, and there you are. So this is North Pole, and this is equator. So what are the apparent weights? So I'm going to do something kind of wild. I'm going to make sure we know exactly how fast the Earth is rotating. So we know that the Earth, the equator of the Earth, travels basically 360 degrees in sort of 23 or 24 hours. It's actually 23 hours, 56 minutes, but that's close enough. So we're going to say V at equator is actually 2 pi times the radius of the Earth divided by 24 hours. Again, 23 hours, 56 minutes is really what takes a is what a sidereal day is. That's really the one that matters, but that's not a big deal. So what I'm going to do is I'm going to look up just out of caution. I'm going to look up the radius of the Earth. And the radius of the Earth in meters is in fact 6.38 times 10 to the 6th. .38 times 10 to the 6th meters. So V equator is going to be equal to 2 times pi times 6.38 times 10 to the 6th meters divided by 24 hours times 1 hour in the bottom is equal to 3,600 seconds in the top. And that'll be our conversion. So now I'm going to do that calculation real quick. 2 times pi times 6.38 e to the 6. And then I'm going to divide that by parenthesis 24 times 3,600. And that gives me 463. Actually, I might as well say 464.0. meters per second, which, by the way, 464. I'm going to convert it to miles per hour just so you have a feeling for it. So 464 miles per hour, or excuse me, meters per second. Is the equivalent of 1,038 miles per hour. That's kind of interesting. It does go 1,000 miles per hour, believe it or not, in just rotating around the Earth. So I'm going to first handle the equator case. So solution. Equator. So at the equator, we're going to draw a free body diagram again. Okay. I'm going to put the mass here is M. And what we have is a force pushing outward that is in fact, the positive direction. And that's the force supplied by the scale. So I'll just call it Fs. It's also a normal force. I mean, if you're really wanting to see what this is the same thing as a normal force, just this time I'm calling it a force on the scale. So we can figure out that, oh yeah, that obviously is the weight that it's going to read. So that's what we're shooting at here. Now, what we also have is the weight due to gravity pulling this way. And that, of course, is in the negative direction. But we also have that the object has to accelerate in this direction with A equal to V squared over R. So the summation of forces in the X direction is all we've got to do. Summation forces in the X direction. That's going to give us Fs minus mg is equal to negative, because notice the acceleration has got to be in the negative X direction, negative m v squared over r. So the force on the scale is actually going to be negative m times v squared over r. And when the mg comes over there, that'll be a positive, and a negative times a negative gives you a positive. So I have to put a negative here, and that would be just g. Now we're really going to want the magnitude, but it's got to come out negative. So with this, I'm going to get negative. Let's say the person has a mass of 100 kilograms. So let's say I'll turn it to green and say m, just so we'll have a fixed figure. I'm going to say that's 100 kilograms. So negative 100 kilograms times, we already figured out the velocity is 464. And that's going to be squared, of course. I could have written that smaller. That would have been really nice, huh? 464 squared, and we'll leave off the units here, over the radius of curvature, of course, is the Earth's radius. So that's 6.38 times 10 to the 6th, and then minus 9.80. So when I do that, I'm going to get 464. That's going to be squared. So as soon as I find my square button, there it is. 464 squared. And then I'm going to divide that by 6.38 e to the 6th. That's going to give me negative 100 kilograms times 0.0333745 meters per second minus 9.80 meters per second, which is going to give me Dang it, this decimal point will not push. So now I get negative 100 kilograms times negative 9.766 meters per second every second, and multiply that by 100. And you get, in fact, the weight is going to be 977 newtons. Okay. Now, normally mg is the weight, and that would be 100 kilograms times 9.80 meters per second. And that gives you, of course, 980 newtons. So you actually lose weight at the equator. So I'll box that off. With the other one, you can see at the North Pole, okay, I'm going to draw a free body diagram again. Okay, I'm going to put a mass there, and it's going to be a mass M. There's going to be a scale force pointing up. There's going to be a weight pointing down. And in fact, there is no need for centripetal acceleration at all, because on there, you're just sitting still while the universe or the planet revolves around the axle that goes right through you. So there's no acceleration. So you end up getting F scale minus mg is equal to 0. So the F scale is in fact 980 newtons. And I'll color that in blue. Any questions on that? All right, well, let me do one more problem, and because we only got about 7 minutes, but what I'm going to do, this might look somewhat familiar to you. Hopefully it does. There's a pulley.
Oh, Professor,
Yes.
can you go back to the previous page for a moment? I'm still trying to copy everything down.
Yes, no problem.
All right, thank you.
No problem.
You mind going to the
So-
previous page before that one? Because I was still trying to copy down the notes from the previous.
Yeah, and it will be on my Google Docs too. Actually, I normally do it right after class, so you can download it immediately after class if you want.
All right, thanks.
No problem. So let's say we have a pulley like so, and it's affixed to a wall in a corner. Okay. And now what I'm going to do is I am going to put a box right here. And that box has a mass of 20.0. 20.0 kilograms, and it has a force on it, F, which we're actually wanting to know what force that must be to actually cause it to accelerate. It's going to have a string connecting it, and then a string connecting it to another mass sitting on top of it, and that mass is 10.0 kilograms. And everywhere the static friction is 0.50, and the kinetic friction is 0.30. Okay, so what you want to know is what F is required to make the boxes accelerate. So in other words, I'm going to assume the friction force is at its maximum, and then the acceleration will be exactly 0. because at that point, I said in class today, rabbit farting near it would actually push it and make it go. Okay, so it's just you're bringing it right up to that cusp. So first off, I'm going to draw the free body diagram. So here's our solution. By the way, in the problem that's like this in your homework, you then add 10% to that force and then work it out again with the kinetic friction, and that'll actually give you the acceleration. So that's something I'm not going to be able to fit in here, but I can at least do this first part. So I'm going to draw a free body diagram for the small mass first. And this is going to be 10.0 kilograms is right there. I have acting on this a normal force that I'm going to call Fn1, because obviously we're going to have other normal forces. I'm also going to have a negative force of 10 kilograms times 9.8. So that'd be 98.0 newtons pointing downward. Now the box under it is being pulled to the right, and the box itself is being pulled to the left. It's being pulled to the left, in fact, by tension. So this is T, but there's also going to be a friction force from the box below that's going to be equal to mu static times Fn1. That's all the forces acting on that. So we can say the summation forces in the y direction is going to give us Fn1. And like I often argue, it's going to have acceleration of 0 in the vertical direction. So that's Fn1 minus 98.0 newtons is equal to 0. So we know that Fn1 is actually equal to 98.0 newtons. So that's helpful. That's something we'll need. I'll call that 1. The summation forces in the x direction, that's going to be something else. I don't know why I switched to red. I'm going to go back to green. So in that case, we're going to have 0.50 times 98.0 newtons, because I'm making use of Fn from above, minus the tension is equal to 0. So from this, we can tell the tension must equal basically what, 49.0 newtons. So that's going to be fact 2 that we know. Now I'm going to draw a free body diagram for the other mass, and this is where things get kind of crazy. You've got to think a lot about what's going on, but I'm going to draw that and that, and we'll put a little mass in there. And I'm going to say the mass is 20.0 kilograms. Now acting on this mass will be a Fn2. That's the normal force applied by the floor, or the bottom right below the box. But remember, this box provided the normal force N1 on the 10 kilogram mass. And according to Newton's third law, that means the 10 kilogram mass applies the exact same force, but in the opposite direction. So we're going to get a force of 98.0 newtons downward. And that's just due to the Fn1. Okay. We're also going to have the weight of this guy, which is 20.0 kilograms times 9.80 meters per second. So that we know that 2 times 9.8 is 19.6. So 20 must be 196 newtons. So we have that. We've got those two forces acting downward. That really should be it. But here's the kicker. We actually have a force F that we wish to know is pointing to the right. And then we've got the friction force from the object above. It's trying to pull it to the left while it's trying to go to the right. So we're going to have a 10 kilogram mass applying the same friction force that it had on it is going to be applied to that block. So notice the friction we drew in the previous diagram is to the right. So this friction must be to the left. And in fact, we know it's 49.0 newtons. So this is F1 equals 49.0 newtons. We know the tension is going to tend to pull it backwards as well. And we know that that tension is 49.0 newtons. And then we know also that it's got its own friction. And that friction we'll try to draw in here. And that's F2. And F2 is basically going to be the normal force into times mu. So now we can say for the y direction, we're going to have F into minus 98.0 newtons for Fn1, minus 196 newtons. That's for the weight itself. And all that has to equal 0. So Fn2 is going to be 98 plus 196. If I added 100 to 196, it'd be 296, but I'm 2 less than that. So it's going to be 294. So 294 newtons is the normal force. I'm going to use that and I'm going to call it 3. Now I'm going to do the x direction. And again, we're just working out the maximum magnitude of the acceleration to find out what the force will be. In this case, we have the F that we want to know. We have minus 49.0, minus 49.0. Notice one of them's for friction and the other one's for tension. And then minus 0.50 times 294, because that turned out to be the normal force. And that's all the forces acting on it. There's 3 in the back and 1 in the front, and that will just be equal to 0. So we can in fact say that F is going to be 49 plus 49 plus 0.5 times 294. And that gives me 245 newtons. And that, of course, would be number 4. And that's really the answer we saw. So that's how you go about figuring out what force is required. You got to count all those forces and be very careful. Now, the second part of the homework problem is let F be 1.10 times this force, so 245 newtons, and then work it all out where you're now using mu static instead of mu kinetic. So that's the only difference. You have to redraw the diagrams. You have to figure out which equations are right as they are and which equations aren't, because you're applying a larger force. That's going to be a bigger thing, but also because you're accelerating it, you're now getting a mu that's not equal to 0.5, but rather that's equal to 0.3. In your case, I think it's 0.65 and 0.33 or something like that. But anyways, I just wanted to show you that. Of course, the time is up. Y'all are free to go. You're always free to go at the end of time. I often will talk over, and you'll at least catch it later when if you look at the video, you can at least look at the last few minutes. But you guys are free to go. I'll wait for the last one to leave before I do. Thanks for coming, everyone.
Have a good evening.
You too, Jamie. Anybody else have any questions or anything?
Have a good night.
You too, Joseph. Thank you. Lauren, you there?
Yeah, sorry, I was just writing a couple more things down.
No problem. Just checking. William McKenzie, are you there? I don't know why I said your last name. David Burke, you here?
Thank you for Professor.
You're welcome. I hope it helped you.
Thanks.
Contact me if you're having difficulties. Trust me, if you're having problems, everybody else is. So I just, want y'all guys to remember, hey, you're paying me to be your teacher. So feel free to contact me if you're not understanding the stuff I do.
Yeah.
Teaching over the internet's hard.
Yeah, I agree. But yeah, I definitely want to go to some of your office hours because I'm not great at calculus. And I'm actually like going through Calc 2 right now.
Right.
I'm just trying to get it all straightened out, but
yeah, and this course is really one that I take some pride. Have a good one. Thanks for coming, everybody. Appreciate that. Remember, ask me questions if you don't understand the stuff. If I'm doing some calculus, you don't know why I'm doing that calculus, make sure you ask me. If you have some problems where, this is an internet class, it's hard, and you're not getting enough out of it, make sure you let me know, come to my office hours or whatever. You can even just I'll set up a Zoom meeting and we can do some one-on-one stuff, or you can meet me during my office hours, which I've told you about before. So have a good one. Bye-bye.